Good morning, students. Uh, Myself, Dr. Moumita Sahoo, working as assistant professor in the Department of Applied Electronics and Instrumentation Engineering. So, today I'm going to discuss about a topic which is related to signal. So, we'll start from the basic. So, introduction to signal. Now, this chapter or this topic basically is very much needed when you study network theorem or circuit theory. In third semester, usually you study, and other subjects like signal and systems, and also you can consider the subjects like digital signal processing. So, whatever. Okay, so without giving any other introduction, just started. Then what is signal? So signal is defined as a function of one or more variables. So variables in the sense you can consider time as a variable. Sometimes you can consider frequency as a variable. Okay. So signal is defined as a function of one or more variables which provides information. Say, if I consider that you want to monitor the temperature of your classroom, so in that case, we have to use some sensor which will measure the temperature. Say you have set some span. So say from 10 to 12. Now, in that span, the temperature is increasing. So you from that signal or from whatever the signal you will collect from the sensor, you will find the temperature is gradually increasing from 10 am, after that 11 am, 12 am. So temperature is gradually increasing. So you are getting one information that from that signal you are getting one information that temperature will increase as when the time is 10 am, after that 11 am and 12 am, etc. And after that, if you keep on taking this, if you keep on monitoring this temperature, you will find that the temperature after sometimes like after 2 p.m. or 3 p.m. you will find the temperature again start decreasing, and night it will decrease further. So you are collecting some valuable information from that signal. So in mathematically we can define the signal as a function, like we say na f of t. So f of t means it is a function or it is a signal f which depends on time. Now here one signal also has been shown, that this is the amplitude side, the time side. Here you can see the maybe any signal, the amplitude is initially increasing, then decreasing, then suddenly increasing. Okay, so we are getting some information. So another type of signal is also possible, like this one. Say this is time scale, this is the amplitude scale again, where we know there is some time, for some period the amplitude is fixed, there is a sudden change and the amplitude is very low, again there is sudden change, again the amplitude is very low. We all know this is a square wave, and this is any, you can't represent this type of signal, means there is no such expression available for this arbitrary signal. This is an arbitrary signal and this is a square wave. We all know we can represent with some expression. Now, so for a function, when you say function a, so in this expression, so when you are saying that it depends on variable, so these variables are the dependent variables. So for this two, here time is the independent variables, and here dependent variable is your amplitude. So there are mainly two variables, dependent and independent variables, where time is the independent, where time will keep on changing, and depending on that the amplitude will change. Any example you can consider. Now, so there is some examples are shown like a voltage or a current in an electronic circuit. In an electronic circuit, we often measure voltage, current using ammeter, voltage using voltmeter. And what about the data we are collecting? If we consider it for considerable time, so it becomes a signal. Now, in other case like position, velocity, acceleration of any object in car, that also you can measure and you can represent them in the form of signal. Like, and also force, torque, this is also possible. Flow rate, temperature, just now I said, liquid or gas pressure, okay, in a chemical process, or their label, this is also very much important. And nowadays we are constantly talking about digital image, digital video, digital audio. These are also a type of signal. Now the stock market index or the rainfall chart, these are discrete in nature. So this is also another type of signal which we'll discuss in the further slides. Now in biological signal or biomedical signal, so ECG signal, we all know about it, blood pressure, heartbeat, so all are signals with different types. Now let's discuss about the dimensionality. So if the signal depends on only one independent variable, then it's called one dimensional signal, mainly the speech or the audio, or that which I give the example that the temperature signal, all are one dimensional signal. Now when you are clicking some photos or the MRI signals, these are the two-dimensional signals. So mainly images are the two-dimensional signal, where this is the x coordinate and y coordinate. These are two independent variables. Now if you consider video has again three-dimensional. So the single dimensional or multi-dimensional, both are possible. Now coming to the classifications of signals. So mainly first we classify the signal depending on its nature. That means whether the signal is continuous with time or discrete with time. See, there are two images are here, and in this figure, say time is continuous, and at any point of time it is 0, then you can take the value at 1, 2 or 2.5, 3.1. At any point of time you will get some value. But in discrete time signal, see, we are getting the value at 0, which is 3, which is 2.5, or at 1 again we are getting 1 values, at 2 again we are getting some values, but between 1 and 2, if I consider 1.1, 1.5, but there is no such value. So we can say that here time scale is discretized. Okay, so time scale is discretized. So how we can say, or we can also further say that this axis is the time scale or the independent variable. So this axis continuous or discrete. Depending on that, you can classify a signal whether it is a continuous time signal or discrete time signal. So these some examples are say temperature curve, voltage curve, or any, if you consider ECG signal, so all are continuous in domain. But the discrete time transaction, nowadays we most of the time we do that Paytm, Amazon Pay, so all this and you can have the history of transaction. So when you go to when you check this transaction, these are the example of discrete time transaction, because there is a gap. It is not discretized way you are paying something. Okay. A stock market index, this is also discretized in nature. Rainfall chart, today maybe is raining, tomorrow it will not rain. So depending on that, we have to make a rainfall chart also, so which is a discrete time signal. Now another one is the analog and digital signal. So analog signal can be both, means continuous time and discrete time both. Okay. So so first of all, if we take a signal, then you have to divide into two parts: analog signal and digital signal. Under analog signal, both are coming. Maybe continuous time, maybe discrete time. Okay. And under digital signal means that this y-axis or amplitude axis, basically it is quantized. First it is quantized, and after that we have to label or encode each value in a two level, means either low or high, or 0 or 1. So first you have to quantize, see, we have to discretize the y-axis or amplitude axis also. This is called quantization. So now I'm not going to discuss in detail because it's not needed for this topic only. And then so first we need the quantization, means we discretize the amplitude scale also. And after that, each label, so this label, if we consider that this level is low, is something compared to some threshold value, so you can consider this is a low or 0. But if you consider this one, it is compared to some threshold value, it is more than that, then you can consider this is high. So then this is total signal to each label we are encoding into two levels, either low or high. So this is basically we are converting a signal into a digital signal. So this is some as a continuation of the last slide. This is called continuous time analog, means this is an analog signal where time scale is continuous. This is also an analog signal where time scale is discretized. Okay. Now this signal is a continuous time digital signal, means this time axis is continuous, but it has only two state, lower and higher, low state and high state. So you can say continuous time digital. Another one is discrete time digital. Here time scale is discretized, but it has only two state, low and high. Now the classification of signals. So first of then periodic, aperiodic, I think all you know because we are starting from school level. So in this case you can see periodic means if we say the signal is starting from here or here, so this signal will repeat itself after this point. Again this signal will repeat itself after this point. So we have to consider one full cycle. For that, how much time period it takes. So that is called the time period of any signal. So in this case, see, the time period is t. See, from here to reach here, from there after this point again it will repeat itself. So the time period is your t. Okay. So means one signal is repeating itself after certain intervals, which is your capital T. So in that case we can say signal is periodic. If it is not done, then we can say it is aperiodic. So thus there is some formula, x of t equals to x of t plus n into capital T. Capital is T is the time period. Now n means if I consider the first cycle, then the second cycle, third cycle. So n is a positive integer. Now this is the example of discrete time periodic signal. Here you can see, if I consider this one is started at 0. Okay, after that the 1, 2, 3, 4. So this part is your one cycle, you can say. After that again it repeats itself, 1, 2, 3, 4. Here also 1, 2, 3, 4. So what should be the periodicity here? Here periodicity means from here to here. After that it will repeat itself. So here periodicity is 1 gap, 2 gap, 3 gap, 4 means after 4 samples, the discrete signal repeat itself, 1 2 3 4. After 4 samples, again it will repeat itself. So we can say here the periodicity is 4 for discrete time signal. Means you have to count the samples. These are called samples, and here you have to check that how much time is taking to complete one cycle, how much time is taken as well. So the smallest period with which a signal is periodic is called the fundamental period, all you know, and this is called fundamental frequency also. Now even an odd signal, again we know if this is a signal, and if you fold this signal along y-axis, then you can see the right side is superimposing on the left side. That means we can say the right side is the mirror image of left side. So in that case we can say the signal is even signal. But if it is not done, then we can say signal is odd signal. Here you can see one example. So if you fold it along y-axis, the right side and left side is not superimposing on each other. So this is a odd signal. Same is also possible for the discrete time signal, discrete time analog signal, if I want to be specific. Then see, if I fold it along y-axis, see all the samples are superimposing on each other. So this is your odd signal. Now this side is odd, this side is the positive T, and if I consider the left side is a negative T. So if I write x of t equals to x of minus t, that means right side of t is equals to left side of t. If it is possible, then it is even. If it is not possible, then it is odd. And one extra minus sign is there. Same for the discrete signal also. In discrete signal, the x-axis is represented by small n, which is called time index. Okay, and this is discrete in nature, or this is the integer. Now the signal you can decompose. Every signal you can decompose into two parts, even and odd, or even component or odd component. So an FT is a combination of even part and odd part. Now this even and odd part, if you further decompose, means if you write this way, you can write this way. So this is the simplification. So if you do this, then this part is the even component, half of ft plus f of minus t, where both are same, and odd part is the f of t minus f of minus t. There is a minus where both are not same. So if we can write this way, then we can separate this part, even part and odd part. So the signal, every signal is a combination of even and odd part. Here is some signal. Say if any signals is given, this is also a signal, and this is not periodic signal because there is no repeatability. So this is not a periodic signal, we can say a periodic signal it is. Now this signal also has one even component and odd component. So how we can find out? So this is your f of t. Now if I want to find f of minus t, means just we are flipping, just means right side become left side become right side. So f of minus t we are getting. Now if I add them, we will get this signal, but we know the component is half of. So here the amplitude is maximum 2 now, so actually total amplitude will be half. So that should be an even component. Now in the same way, again after drawing ft and f of minus t, if you subtract them, then you will get its odd component and then half it. So this is the process by which you can find out the odd component and even component of any arbitrary signal. Just draw the ft and then find its this is actually called reversing. I will discuss later. So f of minus t by flipping the positive side left side and left side at right side, and then add them and then get it half. So you will get the even component. If you subtract them and then get the half portion, then you will get the odd component. Now coming to the signals operations. So signal operations mainly useful means just we are saying f of minus t, or sometimes the signal is in present condition, or it is delayed version, or it is advanced version. So in that case also we can consider the signal operation is important. Like so consider this first signal. This is the original signal which I have received from the sensor. Now after that we need to do some processing. So we can shift the signal at right side, because or we can shift the signal at left side. Now when we are shifting the signal at right side, say it's written this is called delayed and it is called advanced signal. So why it is say delayed signal and why it is advanced signal. So suppose this point, okay, this is the origin of this signal. So say the point is at 10 am, that means your class, so suppose your class started at 10 am. Okay, now you say some students entered this class at 10 am, so this student is on time. Now in the same class some students entered at 10:30, then means that student is late by 30 minutes. We can represent this way. If it is your 10 am and so this it's a time scale, so this can be at 10:30 if we assume. So if you compare this original signal and this signal, so we can say this signal is the delayed version of this one, or the student is late for the class by 30 minutes, okay, came late. So that's why this signal, when I shift a signal at right side with some amount of time, then the signal is called delayed signal. Now in the same way, if the students come to the class at say 9:30 or 9:45, that means the student is advanced. Yes, the student reached to the class before time. Okay, means 9:30. So compared to this signal, that means this is the advancement position, advancing position. So we can say when we shift the signal, if I shift the same signal to the left side, so if the signal is starting at 9:30 suppose, so that means shifting a signal at left side means the advancement of the signal. Shifting a signal at the right side means a delayed signal. So it will be easy if you consider by time. Okay, just now I said now this is 10 am and the students came at 10:30. Then was not very serious students. If the student is very much serious and very much interested to do the class, so in that case students came early at 9:45 or 9:30, then means is the advancement, is the delayed compared to the original signal. So you can write in another way also. See, this is the original signal you have written at f of t, and the advanced signal you have written at f of t plus t, and the delayed signal you have written at f of t minus t. So why you have written plus and why you have written minus? See, the present state, so suppose t equals to 10. Now the past value, if I want to write f of t minus 2, t equals to 10, so it becomes f of 8. Now if you consider, if you compare with 8 and 10, so 8 is the past coincidence or past value compared to 10, so this is your past value. Now if I write t plus 2, so it becomes f of 12, sorry, it becomes f of 12. So in that case, so 12 and 10, if you compare, so 12 will be the future value compared to 10, okay, or advanced value of 10. So when I write f of t plus 2, that means it is used for the future value or the advancement value. Or when I write f of t minus 2, so is used for the past value or the delayed signal. Okay, that's why a minus is used and here plus is used to represent advanced signal. So students, now I am ending this slide and ending this topic here, and I'll continue some next part of this same lecture in the next session. Thank you.